chapter's called Kinetics. And we've heard the word kinetic before when we talk about energy. Kinetic energy is the energy of motion. How fast something is going dictates its kinetic energy. Can we apply the same concept to this use of the word kinetic? Kind of, yes. Reaction kinetics has to do with how fast a reaction is going. Now, I have a visual that I want to show you, a graphic. This is used a lot in chemistry to describe reactions. It's a graphic that describes what's happening with the energy of a reaction. And with what you've learned so far in chemistry, you should be able to understand what this thing represents. In a reaction, there's reactants. That's what you're starting with. You don't have any products yet, it's all reactants. And so you put them together, and the reactants will, over time, maybe fast and maybe not fast, change into products, assuming that this reaction is going to happen. So the reactants have a certain amount of energy. I just erased some of the energy. That's not going to help. Okay, how about I just do that? Oh, don't do that. Oh, man, well, I'm a mess. Okay, so anyway, what I had before, I don't know if I can undo that. I'm not going to bother. But there's an increase in energy and then a decrease in energy. It's like this hill to climb. What does that hill represent? We start with reactants, right? At the beginning is reactants. The reactants have... Asta, go ahead.
The activation energy.
That is the activation energy, yes. Let's see, when we were talking about enthalpy, at the very beginning of our discussion of enthalpy, delta H, we talked about how when bonds break, energy must be put in to get bonds to break apart. That's exactly what's happening here, is the activation energy is the energy required to break the reactants all apart. Once things are broken apart, then can they rearrange and make something new, and we start making the products. But the reactants don't just suddenly become products. They have to break apart themselves and then physically rearrange. So that's what this increase in energy is. And I hope that you remember me kind of making a big deal about the fact that that in order to break bonds, energy must be put in. And that is a very big deal in chemistry. And that's what this represents right here. Whoop! We're going up, and we get to this top of the hill. The distance between the reactants and the top of the hill, that's the activation energy. Once they're all broken apart, at the top, we don't have the reactants anymore because they're broken apart. We don't yet have the products because they haven't been made yet. So what is it? We call this, there's two different names that we use for it. It doesn't matter which you call it. It's called either the activated complex. Activated just means that everything's broken apart and nothing really is made yet. Or it's sometimes called the transition state. Transition state is more descriptive, I think, because it's just an in-between phase. So then, why are we going down the hill? It's because new bonds are forming. And when bonds form, energy is given off. When you take a look at this graph, is energy overall being taken in or given off? It is being taken in, yeah. And how do we know that? Because the reactants start with a certain amount of energy, and at the end, there's more energy in the product. So overall, this thing has to have had energy taken in. This would be an endothermic reaction. Even exothermic reactions, all reactions are going to have this hill because they do have to originally break apart and then make something new, so there's always the hill. So you see how it's broken up. Thermodynamics deals with the beginning and the end. You know, we talk about state functions, deltas, things like that. That's what's happening, or that's what we care about with thermodynamics. Now the kinetics component, we're going to be describing what's happening during the reaction. It's going to describe the activation energy of the reaction, how fast the reaction's going, that kind of thing. So down here I just have just a quick little general description. Thermodynamics overall, what's happening with the energy. The kinetics is the how. Amber?
So, has something to do with state functions?
Well, the thermodynamics does, yes. There's going to be no mention of state functions in the kinetics. Yep. There's really no, are there any deltas at all in kinetics? There's delta G, of course. There's always delta G now. Not really, no, it is not about state functions at all. Because the pathway, kinetics describes the pathway. So yeah, I mean, the whole thing about a state function is it's independent of the pathway, but that's what the kinetics is going to do for us. Katie?
Just to clarify, for the graph, the hill is the kinetics part, and then the other stuff is the
Yeah, the beginning and the end is the thermodynamics. I have messed this thing up badly, and now I can't fix it. Yeah, from the beginning, or from the beginning to like where it starts to go up, that's what thermodynamics deals with, and at the end is what thermodynamics deals with. Yeah, and the hill part is the kinetics. Yeah.
So if we have delta G, then do we also have other deltas in order to find the delta G?
Gosh, I'm racking my brain. I don't think we're going to deal with delta 8. Did I just say that? We're not going to deal with any deltas except delta G. I can't think of any others that we're going to have. Yep. The activation energy is, well, yeah, there's going to be different things that we'll do, but no other deltas that I can think of right now. We ready to move on? All right, so far so good. This is not hard to understand. Now, when we're talking about how fast a reaction is happening, there's multiple ways to describe the rate of a reaction. In this chapter, I'm going to use generic terms a lot. I won't use actual chemical equations all the time. I'll just like A yields B or A yields products or whatever. You'll see this a lot in here. So A is the reactants and B is the products. We can describe how fast a reaction is going if we know how fast the amount of, I'm pointing at the reactant, if we knew how fast the reactants were being used up, we'd be able to tell how fast the reaction was. That would define how fast the reaction is going, is how fast that's being used up. Or the B is being made, that's what the products are. If we could measure how fast the products were being made, that would also tell us how fast the reaction is going. Would these two rates be the same? Would the rate of A being used up equal the rate of B being made? In the reaction that you see right here, would they be the same? If these are a 1-to-1 ratio, yes. Yes, they would be. Because as A gets used up, B is being made, and the rate of A changing is the rate of B changing, so they would be the same. Except this is actually getting used up. That's got a negative slope if we're measuring its concentration versus time. This, a B, is going to have a positive slope. So, you know, you can use the words there, consumption, formation, to figure out which is happening. Okay, and now there's graphs here. I don't know. You're not going to have to duplicate or do anything with these graphs, so I don't know if it's even worth writing them down. But just as a visual, A, it would be what the reactant is doing. We have to start with reactants in a reaction. They'll get used up, so down it goes. B, we assume that there's no product to begin with, so we start at 0, and it goes up.
Is the rate always the same?
What if, I'm going to answer your question. What if the reaction said A yields 2B? What would you be able to say about those two graphs? If it was A yields 2B. Would you agree that whatever A's slope was going down, B's slope going up would be twice as much as A's slope going down? Yeah. So no, they're not necessarily always the same. But if they're a 1-to-1 ratio, yes, they are.
No, I'm not saying, just for A. Like, does it change over time?
What do you think? As some of A gets used up, does the rate of the reaction stay the same, or do you think it changes? take a guess. I'll let you guess.
Is this the same?
Kind of reason through that. You remember how we talked about reactions going to equilibrium? So if this reaction went to equilibrium rather than going to completion, it wouldn't go all the way to 0, would it? Because if it went to 0, that would mean the reaction goes to completion. It never stops until we ran out of it. If it stopped at equilibrium, that means there would still be some A and still be some B. Or there would be some B at the end. Would the rate of A be the same the whole way? We'd have to level off, wouldn't it? A would start by taking a dive, down it goes, down, 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 but then it would eventually level off, and over time, it would just wind up staying the same if it got to equilibrium. So the answer to your question is no, it doesn't stay the same. And when we measure the rate of a reaction, normally we just measure the very beginning rate of the reaction, because as soon as we start to use up some of A and we start to build up some of B, then we've got the reaction will be going both this way and that way, and the rate will be affected. The more it's going back the other way, the more the rate is screwed up, and we can't measure it as well. So normally we just measure the initial rate of the reaction. And we'll see that more as we go through the chapter. It's a great, I like your forward thinking on that. That's good. Okay, so anyway, we would calculate the rate of the reaction based on how fast the reactants are getting used up. And don't miss this part. The rate would be negative delta concentration of A over time. You see that little negative sign up there. Don't miss it. Is that on the screen, Katie? Where, now the rate has to be positive. You can't have a negative rate of a reaction. The concentration of A change is going to be negative, but the rate itself is positive. So A's concentration change is negative, so I have to put that negative sign out in front of it to make it a positive rate. And then if we're looking at the formation of B, then the B is increasing over time. It would just be positive anyway. The reason I'm showing you both A and B is, let's say that we have a reaction, that we have some reactant A that's a clear liquid, and as it reacts, we can't really see anything happening to it. It would be hard to measure how its concentration is changing. However, if its product in this reaction is a gas, maybe we could have some setup where we could measure the pressure of the gas as it's made. Then, in that case, then it would be easy to measure the rate of the reaction by measuring how the pressure is changing over time. So it depends on what the physical states are. Sometimes it's more convenient to measure the rate of the changing reactants. Sometimes it's easier to measure the rate of the changing products. We'll have to do this sometimes. Now I've got a reaction in which we have one reactant and then there's two products. One of the products is made twice as much as the other one. And we could see as A gets used up, A's concentration is going to go down because it's going to get used up. B is going to get made, and the rate that A goes down is going to equal the rate that B goes up because they're a 1-to-1 ratio. But notice the C. The C is going to be made twice as much or twice as fast as B is made. So the balanced equation is going to allow us to figure out the rates of the reaction, or the rates of the different components of a reaction. This is super easy. It's like a stoichiometry effect, and we're so good at stoichiometry in here that this. Don't try to look into this and make more of it than it is. It's very simple. Just use the coefficients. That's going to allow you to know the relative rates. Relative means compared to others.